Hello. This orthogonality and norm that we have been able to define using the inner product is going to help us define orthonormal basis. And why do we want this kind of basis? Is because then many things become much easier once we work with orthonormal basis. You already know some typical example of the orthonormal basis, the Cartesian frame, right? The j of the plane, the ijk of the space. These are all orthogonal bases, orthonormal bases, and you already see why it makes all the calculations much easier in those kinds of bases. So again, the idea is to extend this concept to any linear space because we can now we know how to define norm, so we know how to say that something has norm one, and we know how to define orthogonality, so we know how to say that two items are going to be orthogonal to each other, right? So let's start with a nice definition. So we have a vector family. So we've got some EI for I belongs to I. It means that I've got some vectors E1, E2, etc. It can be a finite family like this or an infinite family like that. If we go on, and we will say that this family is orthogonal if they are orthogonal 2 by 2. Okay, if for any ij I've got that the ei ej are orthogonal, meaning that their scalar product is equal to 0, and we will say that it's all orthonormal. Well, you get that if all the items have norm of equal to 1. Okay, let's see what we can do with these ideas. All right, first thing, we will get the generalized Pythagorean theorem. Well, it's the same one as before, but with as many vectors as you like. Well, if you have, let's say finite, let's begin with finite. The sum of all the vectors, the norm of the sum of the vectors is the sum of the vector square, or the norm square. Well, try it. Okay, try it by yourself. It shouldn't be too much complicated. Maybe you can do it by induction, or you can write it by induction, assuming that you have three vectors. So we did it with two. That was the Pythagorean theorem. You can try it with three vectors, see what it changes, and then, well, what does it give you if you do x1 plus x2 plus x3 scalar product with x1 plus x2 plus x3? Okay, expand that and you will naturally get the result. All right, and now try to write the same thing with n vectors. It doesn't change actually anything. All right, what comes next? An orthogonal family of non-zero vectors is linearly independent. Okay, and in particular, if it is orthonormal, then it is a linearly independent family. All right, let's again. You should pause now and try to prove that. What does that mean? You say, so what do we assume in that theorem? We assume we've got, let's make it finite family. We have this family which is orthogonal. The question is, is this family linearly independent? Okay, so what do we want to prove? We want to prove that if we take a linear combination of this family, so lambda 1 e1, lambda 1, I was right, lambda 1 e1 plus lambda 2 e2 plus lambda n en. If it's equal to 0, does it imply that all the lambda k's are equal to 0 for k equals 1 to n? Okay. What would you like to, what could we do? So it's going to be something that we we know it's going to be a very common techniques. All right, so let's look at that. So we start from this relation lambda 1 e1 plus lambda 2 e2 plus lambda n en is equal to 0, and we take, let's take e1 for instance, and I'm going to take the previous expression. Okay, that's good. That is a combination of vectors in E, right? So let's say, and I'm going to take the product of this expression, lambda 1 E1 plus lambda 2 E2 plus lambda n En, with, let's say, E1. Okay, so on the other side, that should be equal to 0, product with E1, so that's going to be 0. Okay, so what do we get? First of all, how do we prove that? One way to prove this is using the Cauchy-Schwarz inequality. Okay, it seems pretty trivial as a property that if you take 0 with anything, it makes 0. Well, that's something we just said a bit earlier, but you can, it's just we're just applying Cauchy-Schwarz inequality to get that. Okay, so on the right hand side we get 0, and that's the real number 0, and on the right hand side, and on the left hand side, what do we have? We can expand that using linearity, right? So that's going to be lambda 1 e1 with e1 plus lambda 2 e2 with e1 plus etc. Each times I expand by linearity, I get the lambda k times the corresponding ek, so the last one is going to be en with e1, and that should be equal to 0. And now our assumption was that all these were orthogonal, so that means that that's equal to 0. That's equal to 0. They are all equal to 0 except this one, which is not 0, of course, because it's the norm of e1 squared. So I get lambda 1 norm of e1 squared is equal to 0, and as we assume that our family was non-zero, right? So I know that e1 square is not 0, so that implies that lambda 1 is equal to 0. And you can do the same reasoning for all lambda k. You get that lambda k are equal to 0 each time by applying the inner product with the the ek vector, right? So instead of so you would get 0 here, you would get 0 everywhere, except you would get lambda k norm of ek square is equal to 0, and so lambda k is equal to 0, right? So if you've got, well, that's something pretty intuitive. If you've got orthogonality, then it's linearly independent, right? If the family in the family they are all orthogonal 2 by 2, it means that they are linearly independent. Okay, and in particular, you get that any orthonormal family is linearly independent. What are we aiming for here? We want to say that, well, we've got a collection, a family of orthogonal vectors, and we've got enough to make a basis, so we've got a basis, all right? Because I know that they're all linearly independent, all right? That's one of the nice application of this one.